So today I wanted to talk about some of the advances in robotics and mobility that might play into all of this. And so topics I want to make sure I cover is what are we talking about when we talk about a robotic mobility system? Because people, have an idea about what robots are and how that plays into what we actually have when we fly is not always a one-to-one sort of thing. So we'll talk about that just a little bit. And then what kind of advances in technology can affect the access to the Martian surface? And as a different topic, what advances in philosophy can affect the access to the Martian surface? And then just sort of a thought experiment a little bit about if we applied all of these things, what might we end up with at the end of the day? So just to sort of whet your appetite for this, on the left here on the slide is a rendering of the Perseverance rover, M2020. I apologize if for folks outside of JPL, if I call it M2020, your decoder ring is that's actually the Perseverance rover. And then in the inside is actually the Puffer rovers. And in a lot of ways, these two systems represent opposite ends of thinking, both in terms of technology and in terms of the philosophy, particularly in the philosophy of risk. So what we're going through here today might be best captured by the differences in these kinds of systems. So the system breakdown. Now, for folks inside of NASA, this is, you might recognize this as sort of looking like a traditional work breakdown structure for a mission, but I've tweaked it a bit to talk about robotics and specifics, right? So I am going to go through the practice of just reading through this so I can talk about what these things are. And so when I talk about the technologies in a second, you have an idea of what they're being applied to. Right, so when it says mechanical structure, it is kind of what you'd imagine, right? It's the box that these things all have sort of in common. There's a box and you put stuff inside the box. And this is true whether it's a lander or a rover, but you almost always have some sort of box that you put stuff in. And this is largely what that bullet point's about. The mobility subsystem is, traditionally we break this up so that the wheels and suspension, and again, this sort of goes to the Perseverance model, they live in their own sort of subsystem. So now we've got a box and we're going to connect some struts to it and we're going to stick some wheels at the end of those struts. And that's your mobility system. Now we've got sort of a cluster of things that are all sort of subsystems unto themselves. Instrument pointing. So this is kind of the traditional mast that the instruments may rely on, as well as the engineering for navigation. Instrument placement and sampling kind of go together to a certain degree. This is sort of analogous to the robotic arms we would find in a lot of these systems, where we can actually place an instrument for contact, but we can also have tools there that are going to take up samples. The power system, unsurprisingly, you got to get your energy from somewhere. But, as we know for spacecraft, that's a significant question. And a lot of the choice of power drives much of your mission design. Thermal, Mars is cold, but it turns out that things inside of the rovers tend to be hot. And so surprisingly, one of the worst conditions that we run into when operating on Mars is actually how hot we get and whether or not we can get rid of that heat. Actuation and drive control. So these are your motors and gearheads and things of that nature, as well as all of the sensors and electronics that actually run those things. And to some degree, the low-level software that handles that. Compute and data, it's exactly what you think. It's the computer on board. Telecom, another big driver that we don't think about very much, and I'll talk about, but it is one thing to think about how we actually create the signals that run between our surface assets and either orbiters or the Earth, but trying to figure out what goes through the pipes, those data pipes themselves, is a significant question. Localization algorithms, this is sort of the robotics view of things, right? We got to come up with good ways of figuring out our state, where we are on Mars. Perception algorithms fall under a couple of things, but and some of them are akin to the localization, but a lot of it's also understanding the environment right around you so that you know what to do. Flight software, you notice that I called those other things algorithms. Flight software is the thing that instantiate those algorithms. also it's all the other stuff. And there's a lot of other stuff. And we'll talk about that a little bit too. And then the final bit is that the stuff that happens on the ground, both the software tools, but also, and a lot of you have experience with this, is the people, right? So the people are part of this system. And so even though we're talking about the surface system, you can't really talk about the surface system without being able to talk about the people that are actually on the ground trying to interpret what's going on. And so this is a good point for me to say, I'm going to talk about a lot of stuff today that there are other people on this call who know more about it than I do. So I'm going to give you the surface version of it the shallow version of it, but there are other folks that can really fill in a lot of the details. And Abby's pretty smiling about this, I'm sure, because she's had to live this more than a little bit. Okay, so this is kind of the fun stuff, right? This is the tech advancements, and you'll notice I put an asterisk on key areas because these are only some of the key areas. This is not a definitive list, but these are some of the things that might really play into how much emission costs. And one of the interesting things about that is that the technologies that I'm talking about here themselves may not actually be all that inexpensive, but what they might allow us to do is shrink the systems that we need to fly, both in size, actual volume and mass. And as Chris was saying earlier, right, a lot of this is the Matryoshka dolls of, we got to build a rocket, and then the rocket's got to fly a descent stage, and the descent stage has got to carry the rover, and the rover's got something on board it, and then there's the payload. And so all of these things are all gear ratioed together. So if you can shrink any part of that, that allows other parts of that entire chain to shrink. And one of the things that is generally true is that the smaller all of those things are in volume and mass, the less expensive the mission turns out to be because of the infrastructure that's associated with it. It also gives you a lot of flexibility in terms of where you end up landing. Now, I'll also throw in a big caveat here. I'm not going to talk about landing systems, but at a very basic level, the difference between being able to fly an MER style airbag lander and a Curiosity Perseverance class mission comes down to how big that system is in terms of mass and volume. So if we can take either by mission design or by shrinking the package that provides a particular capability from a Perseverance Curiosity size down to Mars exploration size, Spirit and Opportunity, you've made a difference in the type of landing system that you can fly, and therefore, in theory, the overall cost of the mission. Okay, so all that said, here we go. One of the big things is advanced materials and manufacturing. And why do we care about that? Well, we care about that because we can do things like reduce the number of parts. So many people have heard of additive manufacturing. And so instead of screwing together a bunch of parts, each of those parts having to be analyzed in and of themselves, you can actually design them as one piece and use additive manufacturing to create that piece. So over on the right-hand side, you actually see a detail of the Perseverance drill. The Perseverance drill housing, which might have been composed of tens, if not more, parts in a traditional sense, more like the Curiosity drill was. That drill housing is just one big piece of metal that was additively manufactured. And that cuts down, again, on the number of drawings, the number of analyses, the number of hours screwing it together. All of those things matter at the end of the day. The other thing that is here is that we can actually get certain types of performance improvements. So in the other pictures, you're seeing a gear from, it's called a flex spline from inside a particular type of gear called a harmonic. And the two pictures are one of steel and one of this bulk metallic glass, right? It's an amorphous metal. And it has two big advantages over traditional steel. One is that you can actually mold it in the first place. So just like plastic parts are much less expensive to create in number, in quantity than a machined piece, one would imagine that you're going to get bulk metallic glass to do the same sort of cost reduction, assuming you're making enough of them. The other thing is, and this is a little bit more of a nuance, is that they don't actually need lubricants. They don't wear the same as traditional metals. And if we don't have to worry about a lubricant system, then that's a whole area of the design that we don't need to worry about. And that is a chunk of money that makes a difference. It also has some effects, and this is where I'll harken back to Chris and talking about clips. So this technology is hopefully going to be proven out in a flight application on a CLIPS lander in a mission called Cold Arm. And we hope to show that these actuators will work at -180°C without any heating into themselves. So now we can eliminate a second system. So not only are we getting rid of the lubricant, we're getting rid of the heaters that would keep that lubricant warm enough to be effective. So all those things add up. Going down the lower left of the screen, we've got the hybrid structures. So this takes that additive manufacturing and then ups the ante. And you're seeing pictures of the Puffer Rover. And the Puffer Rover, it actually uses a hybrid of its electronics boards and its structure and combines those two together into a single board, if you will, that folds up into the overall body of the system. So now we've got a flat rover. It, again, only needs to be designed once. You don't have to bolt anything together. You do need to put the electronic components on, but it's a much more scalable process. And it's also a much more testable process. So now we can use the techniques we would use to test normal IC boards and be able to do the entire rover system at once. Now that comes with some inherent risks that we'll talk about in the philosophy section, but basically that holds the promise of potentially being able to drive the overall cost down per flyable unit. It also brings up the idea that you can fly more of these things because you can afford to build more of them. We'll talk about that too. And the final bit on this slide is the commercial components. So just as Chris was talking about flying entire commercial systems, here we're just talking about the components that we might be able to buy. And this is a detail of the Mars helicopter electronics and sensors. And we were able to use the Snapdragon, commercial Snapdragon processor, and its the other components within that Snapdragon toolbox. We're also flying, frankly, there's Sony branded cameras that are intended for cell phones. So we've been able to take these, mass-produced items and turn them into something that we can actually fly. And that, of course, comes with all of the attendant cost reductions in that. And as a secret, hidden part that we don't talk about as much is these components outperform a purpose-built flight element. And now, again, it has a lot to do with the way that you look at the philosophy of risk when you're looking at this. So key areas for tech advancement. Number 2, so interoception. This is probably a word that people are less familiar with, but basically it's about how well the system understands itself. We generally do not let the rovers figure out what's going on for themselves. They report all the data, but by adding more sensing to it and letting that sensing feed some of the algorithms, we'll get to in a second, you can actually reduce the overall margins that have to be included because you can basically operate closer to the edge because the picture is much clearer. And so you can allow the system to decide to operate at tighter margins to power and energy and stress and things of that nature. So that is, the better understanding of itself. It understands exactly how far it can push itself, and we don't have to build in some of the margins that we do. That, in turn, feeds the sensing and onboard autonomy, right? So it allows us to get more science dense, right? So the operational tempo goes up. Instead of drilling a hole in the surface of Mars or a drive taking 3 or 4 days to deal with, or longer, actually, you can allow those processes to happen much more quickly if the only thing that's deciding what to do is the onboard autonomy. Potentially, it can lower operational risk because the interpretation that the systems make at in situ might actually be better in some cases than what can be understood by human operators. We haven't seen a lot of this, frankly, in our previous missions, but in research that we've done for other venues, this seems to be a very common thing, is that human operators actually map themselves onto the systems in a way that's actually overall detrimental to the overall capability of the system. And then optimized communication strategy. We talked about this when I was talking about telecom, is that you can actually let that onboard autonomy decide what data comes down. And by deciding what data comes down, it can optimize that to fit fewer bits in that pipe, which means a less powerful system and less time to do it, and actually translates to energy savings for the system as well. Returning down to the lower left for the slide, we've got analysis and simulation for design verification and validation. So we rely on computers a lot for analysis. The descent stage, basically the sky crane, and the fact that it works at all is all in some computer's head, or it certainly was before we tried it on MSL, right? Because you can't test those systems end to end. And the idea is to extend that where you just couldn't to you could, but it's going to be more expensive. And so by moving the design and analysis of a lot of our systems into the computer, and then only doing end tests with the physical system, we can save ourselves time and money as well. Again, that comes with a certain amount of attendant risk and change of philosophy. And then the final thing on this slide are what I call maple seeds. This is a generic term that I use for when we scatter multiple systems around. So the picture you see here is one from the JPL website that is showing a distribution of a sensor network from the back shell of a descent stage to Mars. But it's a general thing. And if we can get more systems out there and scatter them more widely, we can cover more ground. And that comes with a bunch of attendant technology advancements that have to be dealt with, including the basic mobility technology itself, and also how those different systems talk to each other and to any sort of parent craft as well. So examples of that include cadre puffer that I'll talk about in a second. Okay, philosophy, and this might, in a lot of ways, this is probably the biggest thing that's going to make an impact on cost, right? Is the risk associated with open source or not invented here software. There are a couple of examples of this. JPL has developed something called FPrime, which was originally intended for commanding instruments, but is now the code that flies on the Mars helicopter. There's also something called ROS space. ROS, by the way, stands for Robotic Operating System. It's not actually an operating system, for the software geeks out there. It's middleware with a bunch of libraries, but it's an open source system that would allow more people to develop things at lower cost overall and to borrow code from one another. It's exactly the promise of open source in the first place. There is a hurdle there, and you can see that in the graphic, which is the number of defects per 1,000 lines of code, right? So open source projects are, roughly a half defect per thousands of line of code. A Linux 2.6, this was a relatively older study, came in at about 0.6, but NASA flight software is about 0.1. So you can either figure out how to go from 0.5 to 0.6 down to 1.1, or we can figure out how to live with that level of risk. And I suspect the answer is somewhere in between, but it's a significant hurdle to get over. The onboard autonomy versus ground in the loop, it's exactly what you'd expect. So philosophically, how much are we going to handle on board and how much are we going to handle on the ground? And this doesn't have to be a one size fits all for all missions or even one mission, right? We can throttle that up and down, but you have to be able to get to the point where fewer people are involved on an immediate basis in the command of the rover or the other surface system. And that's a point where both science and engineering is going to have to weigh in on that, because both those communities really want to have their hands inside the guts of the systems at all times. An example of what we're doing for Perseverance is actually fast traverse, where we're actually being able to drive further between ground and the loop commands and trust that the rover will actually be able to execute on that. Some other examples are things that you might imagine from machine learning and things of that nature. And again, this is where something that might be relatively black box is going to have to be trusted to carry out key elements. On the lower left now, we come back to simulation and system level testing. This again is, we're going to eliminate a lot of the real hardware component level testing that is very traditional for JPL and for NASA in general, and instead rely on things happening in simulation, but also things happening at the system level. So we're putting off these tests that are relatively expensive in order to save money. And then finally here, we've got the risk associated with commercial components. And a lot of what Chris said about commercial services in general also applies here. So now we're going to rely on the commercial vendor to have done the testing that proves that these components are okay to use. And one of the key reasons for that is the commercial industry changes much, much faster than the flight designs do. And so even if we went back and said, we're going to use this processor on this mission, and then by the time we go back to that processor for the next mission, that processor may not be available, and we're not going to do an entire retest campaign to prove that's true. So we just have to trust the commercial industry to test to a certain level and provide certain compliances. All right, a couple more here. This is more about the types of missions and the philosophy that goes along with them, right? So a multi-vehicle mission. So Cadre is an example of that. That's another CLPS mission. And the hope is to release 3 or more rovers from a CLPS lander and show that they can cooperate to carry out certain types of missions. Somewhat attendant also to Cadre, because it is based on the puffer designs, is the idea that you're just going to allow the capability of the system to drop below what we normally think of in terms of things like obstacle clearance and other things in favor of size, weight, and power. So we're going to basically let these systems be less capable in order to achieve a lot of that. And then you'd ask, well, the problem is, so you drop the capability from the mobility system, doesn't that mean you just can't go as far? Well, not necessarily. And here's where you trade mobility subsystem versus the drive path. And essentially what you're saying is that as we increase our abilities from an autonomous standpoint to navigate the world, we don't have to have the capability of driving over obstacles because we can drive around them. And so you allow that path to increase because you're not driving over obstacles, but it's okay because the total amount of energy is less and the total amount of time is equivalent. And so you get to the goal you're looking for at the same time you would. Again, there are greater risks to that because, no matter how smart you are, if you find a small ravine that you can't physically cross, you still physically can't cross it unless you're a certain size. So going back to that system breakdown, and I touched on a lot of this, but let's go kind of point by point quickly. Right, we have the mechanics and structure, right? So we're going to get smaller and less massive with less design labor and less unit testing because we have these advanced manufacturing methods. On the mobility side, we can get smaller and less massive because we're going to give up on some of the obstacle hazard clearance capability because we're smarter about getting around in the environment. For the instrument pointing, placement, and sampling, we can get, it's similar to the mechanical and structure. Like there's probably not as much to be done there as an overall system, but we can still, just at the mechanical engineering level, we can still make those things better through advanced manufacturing. Power, right? It's a chasing your tail kind of question there. But as we get smaller on the power system, then through reduced margins and things of that nature, then the power system actually gets smaller too. And then it kind of keeps going down because the power system is such an important aspect of the overall mission design and the rover design. Thermal, we might be able to get rid of entirely, right? We can actually build our thermal systems into the structure And so that becomes and just folds into the overall structural problem without any additional work. And one of the things that we kind of joke about there is calling this warm-blooded robotics, right? We can actually build these blood vessels into the system, and just like your own body as a warm-blooded animal, you can move heat from where you don't want it to the places you do, and get system savings in that way. So actuation and drive control, and then compute and data, right? So I lump those together because these are places where we might be able to make a lot of use of commercial components. One of the nice things is that, in fact, there are more people building robots now, and they're not building them for space, generally speaking, but there are more people building robots. And so the number of components that are applicable to robotic applications has gone up, and that allows us to grab some of those things, as well as the compute and data that we were talking about before. Telecom gets smaller because and uses less energy because we're optimizing the transmissions. The localization, algorithms, perception, and flight software, all of those things potentially could be reduced because through open source and inheriting code from other places, and then testing and simulation, we can drive down the overall amount of labor involved. And then finally, on the mission science and planning, that potentially we could reduce the labor and or increase the operational tempo. This is what I call science density, because we were able to put more autonomy on board and also improve the tools in ground ops environment itself. And that brings us kind of back to where we were. So, this system, this puffer system you see here, right? It's a hybrid system. It's using, it is extremely mass efficient. It has a lot of things integrated. In this case, we actually think of this more as a mobile instrument than a rover, because even the instrument itself, in this case, a microscope and a small spectrometer, are integrated into that uniform board that you saw earlier. And it's small, right? So you can afford to send a bunch of these things in the same volume or a smaller volume. So the per unit risk goes way down, but you might be able to cover more terrain with the same sort of package in that way. So, and with that, I think I can turn it over to questions.
Awesome. Thank you so much, Brett. That was super interesting. We do have a couple questions that are popping up in chat. The first one asks if you could give some insight into the risks and safety when using a meta operating system like ROS compared to FPrime, and what would be some of that considerations in selecting one or another? And then I'll ask a question on top of that. Can you define what ROS and FPrime mean for those of us who don't know?
Right. So basically, so let's start with the last question first, which is ROS and FPrime are layers that sit on top of things like the application-specific chips and FPGAs. So all the firmware things that are, maybe reading the image off of a camera or running an actuator and controlling that. So they're talking to those lower level things and moving that data around to the higher level algorithms that do the thinking. So to take an image as an idea, you have a software driver that's talking to the camera, and that passes information up to the middleware that then sends it to a module that does the perception, right? So the 3D stereo imaging and the creation of those elevation maps, right, would happen at the upper level. And so the middleware is what's gluing that lower level stuff to the upper level stuff. And interestingly enough, the way Space ROS has been advertising itself is it doesn't necessarily replace something like FPrime. It might sit off to the side. And in that case, there might be more of the core and core functions that live in FPrime that are more key to the survival of the system. And then something like Space ROS would then handle the communications with all of the non-critical elements. And also those elements in theory would be the things that are more transferable between different missions. In theory, though, that you could also just completely remove something like FPrime and only have ROS, but that's only if you have all of the functions you need. And so there is sort of this trade-off. Now, what's the risk of all of that? Well, that's a lot of things talking to a lot of things. And anytime you have a lot of things talking to a lot of things, it's hard to design it so that it doesn't burp every now and again. And if you have your PC or Apple machine, when it burps, it's just annoying. You reboot and you keep going. When you do it for a spacecraft or a rover, that can be a real issue. And that's kind of, what you're looking for is how testable are those systems and how willing are you to deal with a burp, even if it means the death of the vehicle, if it does it at the wrong time.
Okay, thank you. Next question is asking, is advanced manufacturing on the Puffer rover on a single board, or is it things like 3D printing?
So in this case, for Puffer specifically, it is all on one board. So this is basically a board level, very similar to the standard printed circuit board technology, but with some added special juice in there, mostly in the fact that the boards themselves are more structurally capable than a normal printed circuit board. And because they have these flexible elements between it. You saw in the picture that it has little wings, and those are flex print. So those flex print bits are actually very similar to the thing that connects in your laptop, the screen to the keyboard half of the laptop. So again, basic technologies, but put together in a way that allows us to build this effectively monolithic thing.
Okay. Next question. What is your opinion on leg locomotion for planetary exploration?
Well, I love limbed locomotion for planetary locomotion. So in the research I've done, right, if you can roll, you should roll. It's always the best choice. But there are spots where you cannot do that. And so if we're opening up the idea of access to areas that we cannot currently drive, then you really do want to kind of look at things that can walk around on those surfaces. And that's a very, I think, tractable problem, but it's not one that's going to come at the lower end of the cost range. So that may be that we have a class of systems that are more like the flagship rovers we have now, but are capable of going a lot more at aggressive places to get the science. But I'm always a fan of wheels when you can use wheels, but just maybe wheels at the end of legs.
All right. Next question is, what cultural institutional challenges have you observed with JPL teams trying to scale back process and rigor for Class D or subclass D projects like the helicopter or Marco?
It's an ongoing experience. So with Cadre and Cold Arm, we're going through that right now. We are having to borrow heavily from the way that instrument programs have been developed and the risk postures from those. And one of the key things that happens there, at least at JPL and under NASA standards, is that there's a lot of tailoring. And so that's the way you're driving down the overall cost and time associated with a particular development, is that you're tailoring the review process, you're tailoring the requirements of on components that are allowed to be used and things of that nature. And there's a lot of thought that has to go into that. So I anticipate that the more we do this sort of thing, that those things will actually become their own standards in their own way. So what is a Class D mission? Right now, a Class D mission, something like a CubeSat, and what's a Class D mission for something like a Cold Arm, you would kind of put them in the same boat, but they're really not the same thing in a lot of ways. And so trying to figure out how to do that effectively is going to take a couple of missions to do, I think. CubeSat, that's relatively settled terrain, but we need to definitely do the hard thinking. And that's the part that is a challenge in an environment like NASA and JPL, because we have to educate people. We have to, people have spent in a lot of cases, their careers dealing with, no risk tolerance. and being effectively disincentivized from taking those risks. And the idea that you need to flip that around and incentivize the risk taking is difficult and requires some socialization.
All right, next question. You commented on advantages for multiple very small vehicles for simultaneous operation. Are there also advantages to multi-vehicle simultaneous builds, but perhaps they're not used simultaneously and perhaps they're not small?
Yes. So as an example, Spirit and Opportunity were kind of sold that way. I think we got a marginal improvement over trying to build them sort of as if they were two independent missions, it would have cost more than just those two rovers. But it wasn't a whole lot. I think that the key here is that the reuse of design and components and the testing that's going to be the most important bit of that. So it's really powerful when you can create a flat spacecraft or a flat rover like Puffer, because we could probably build 100 Puffers, test them all, and then choose the 5 that we like the most. And this is basically how boards and chips are done. A mil-spec chip is the same chip that isn't mil-spec. It just got a better test record than the one that didn't make it. So I think that's really where it is. And so, on the bigger scale, it's harder to make the argument that you're going to make that monolithic thing that can be tested and qualified on its own, because it's going to be composed of a lot more parts. But in theory, it's fine. The downside is that, regardless of that system itself, putting it on board a rocket and launching it is going to be probably the larger driver there. And that'll be the upper end of what we can do as a multi-agent system.
All right. And I see a comment from Michelle. One more question, or there are 3 questions that are yet unasked. Should I pick one?
Yeah, let's pick one from one of the students. Let's take it from Ben, and the other folks can ask it in the workshop later when they grab you, Brett. So, and
Sure.
I'm sorry to the remaining folks who aren't going to get their questions, but Ben was next anyway. So.
All right, so go ahead and ask this question. What do you consider the limiting factor in extending mobility autonomy? Is it increasing time between contact with ground station, for an example?
I think the largest thing is actually giving an understanding of the environment to the system. Right now, ground operators interpret a whole lot from the data that they get from the rovers, and giving the rovers the same level, if you will, confidence in where they're going, I think is the big issue. So driving out into that soft sand is going to be a challenge. And so getting the rovers to understand what soft sand looks like, feels like, and otherwise is going to be a significant aspect of that. And this is where, the technologies themselves are not that exotic, but getting them on board something that's going to fit from a power, weight, computational equivalency and all that, and getting on a rocket is, I think, the big issue. So it's not the cutting edge of technology that's the question, it's the cutting edge of application that's going to be challenging.
All right. Thank you. Thank you so much, Brett. Really appreciate that.
Yeah, absolutely. It was fun.